on to confidence intervals for a population mean. So confidence intervals for a population mean. That's the next topic. So confidence intervals for a population mean, and we're going to actually work with confidence intervals a lot. This is something that you'll do in between now and the time you stop doing research. So confidence intervals are very important. So we can use the sample mean, y bar. So this is just a variable, and we solve for the sample mean. And again, we're talking about populations, but we're going to build up to that. We're going to first refer to a sample, but we can use the sample mean and the sample standard deviation, which is denoted by S. We know how to solve for these. That's just the sum from the first value to the last value divided by the number of values. That's the mean. And the standard deviation is the square root of the variance, which is just the sum of the squared deviations, or the average of the sum of the squared deviations. We have to divide by n minus 1, so it's not an exact average. We have to take into consideration the fact that we lose a degree of freedom in solving for the mean before we solve for the standard deviation. Anyways, we can use the sample mean and the sample standard deviation to solve for an interval estimate of the population mean. So we can use this information to solve for a confidence interval. So why would we do this? Well, the mean by itself doesn't give us any indication of how close it is to the population mean. And that's the information that the confidence interval provides. So a 100 multiplied by 1 minus alpha percent, and I'll talk about what alpha is in a minute, but a 100 multiplied by 1 minus alpha percent confidence interval for the population mean mu based on the t distribution, a small sample. In other words, the t distribution is just like the normal distribution. If you look at the normal distribution, it'll look something like this. The t distribution takes on the same shape, but the tails are a little bit fatter. So it's a little bit less precise relative to the normal distribution. We use the t distribution when we work with small samples. We'll talk about that in a minute. But the 100 multiplied by 1 minus alpha percent confidence interval for the population mean mu based on the t distribution can be solved for as follows. We take the sample statistic and we add and subtract the critical t value, and we'll talk about this in a minute. This alpha is popping up a couple of times. We'll talk about it in a minute. That's t raised to the x, that's not t raised to the x, no, that's t. This is t sub alpha divided by t supra n minus 1 denotes the critical t value with the alpha divided by 2 area in each tail under the t distribution with n minus 1 degrees of freedom. And then we multiply that by the standard deviation divided by the square root of the sample size. That's the square root of n. Let me write that more clearly. N. So this is just, and when we do this, you'll see how easy it is. We take the critical t value multiplied by the standard error of the mean of the sample standard deviation divided by the square root of the sample size. So that's the base of the interval, 2y plus the critical t multiplied by s divided by root n. So we're just taking some amount. You can tell that it is this amount. We're taking some amount and we're subtracting it from the mean and we're adding it to the mean to get the confidence interval. And remember, T sub gamma supra degrees of freedom, which is n minus 1, that is the critical T value. So basically what we do is we solve for the critical T value and we solve for the sample standard deviation. We can get that. We know n, so we can get the square root of that. We get this, the critical T value, from the table. We can solve for the sample mean. So all of this information we can easily obtain to create this interval. Alpha is the level of statistical significance. It's the significance level. We get to pick it. And if we want to be 95% confident, we'll say alpha is equal to 5%, which means that we're taking alpha divided by 2 and we're putting 2.5% in each tail under the t-distribution, and we're going to find this range, this 95% confidence interval range. And we're going to be able to make statements like, I'm 95% sure that the true population mean is in between this bottom number, and this top number. So that's pretty amazing when you think about it. We're going to use sample information, and we're going to be able to say something like, I'm 95% sure that the true value is contained within that interval. It's pretty cool. That's what we call inferential statistics, using a sample to make those types of inferential statements. All right, so I'm going to read through example 3, and then we can do that in Stata. So it says, federal gasoline standards state that mu, the mean gasoline mileage obtained by the fleet of all some vehicle, in this case Hawks, must be at least 30 miles per gallon. So those are the federal gasoline standards. You've heard about the CAFE standards. To demonstrate that this standard is being met, National Motors randomly selects a sample of 5 cars and tests them for gasoline mileage. And in the sample, these are the values that we get. So remember, we're working with a set of data Y1 all the way through Y5. And these values are 30.7, 31.8, 30.2, 32.0, 31.3. So these are the values. We've taken a random sample of 5 Hawks, and we want to solve for the 95% confidence interval for the true population mean. So let's do this in Stata, and we can confirm some of these values by hand, but the fact of the matter is we do this using computers. So I'm going to clear the data in memory. So if I type in list, I don't get anything, and I'm going to run this portion of the program. It just says input this variable. These are the values of that variable, end. So this is like a baby program within a program. And now when I list, I've got my 5 miles per gallon, and I can estimate that confidence interval by using the command a means, miles per gallon. And that's that. I know, how easy. Oh, very quickly, we won't do 100% of this program, but there's a portion of this program that I've included just to give you a feel for how important programming is. But for what we'll do, we're nearly done. But back to the confidence interval, let's see. The arithmetic mean, there's also the geometric and harmonic provided. The geometric mean, you've probably heard of that before. You've probably studied it in finance classes, but we'll just look at the, Y bar. And the 95% confidence interval is 30.27 to 32.13. So we're 95% sure that the true population value is somewhere in between 30.27 approximately and 32.13. So in this example, we picked a level of confidence equal to 95%. We picked a level of confidence equal to 95%. So let's solve for this by hand just so that it's clear that it's easy to do. So the only thing that we need is the critical t-value. The only thing we really need to find is the critical t-value. So first we need to get the critical t-value. And we're just going to do this by hand very quickly. We won't do a lot of this stuff by hand because it just takes too long. But we've got this t-table. And again, since it's a t-table, the tails are a little bit fatter than the standard normal distribution. So I'm letting more space exist between the horizontal axis and the density function. This is the density function. And we're looking at the variable miles per gallon, but we'll just put f of t because we're normalizing that. So what is the critical t-value that leaves 2.5%? Let me write that more clearly. That leaves 2.5% under the curve to the right of the t-value. So what's that critical t-value? Well, here's a t-table, and I know that the number of degrees of freedom is equal to 5, which is the number of observations, n minus 1. So 5 minus 1 is 4. 4 is the degrees of freedom. The upper tail probability is 0.025, so I go over to 0.025, and I see that that critical t-value is 2.776. So this critical t-value is 2.776. Let's just solve for the top portion of the interval. Let's just solve for this portion here. Going back to Stata, I can summarize miles per gallon, and I see the average is 31.2, and I see the standard deviation is 0.751663, so 0.7516643. I can just copy it, and I can ask to display that value divided by the square root of 5. So you can do that in Stata, but I've already got it going here in a calculator. So anyways, I'm just going to divide this by the square root of 5 because I have it here, and I get 0.33615. So I know the critical t-value is 2.776. So when I multiply the critical t-value by the standard deviation divided by the square root of the number of observations, the standard deviation divided by the square root of the number of observations is called the standard error of the mean. We'll talk about that in a little bit. And then I multiply that by the critical t-value to get that 0.93316. And then I add that value to the mean of 31.2. So plus 31.2, and voila, 32.133. And that's what we got here, 32.133. There's some rounding error, but that's how we get the top of the interval. We would take this value, 0.93316, we would subtract that from the mean to get the bottom of the interval. So 31.2 minus 0.93316, and we get 30.266. And again, I didn't take that all the way through, so there's some rounding error, but you get the point. It's that easy. Moving right along, let's talk about how we derive this interval. And I won't get into all of the details in the notes. Again, the details are in the notes, but I'll give you guys some pointers. First, let's talk about a sampling distribution. We can get a sampling distribution by taking repeated samples of a population. So suppose we take a sample, we solve for the mean. And then we take another sample from the population and we solve for the mean. And then we do that over and over and over and over. So for any variable, I can take a sample and I can solve for the mean. I can sample and sample and sample. Let's say for college grade point averages, I take 1,000 samples. And for each sample, I solve for the mean. And then I look at how those means are distributed. In other words, I can look at how the means are distributed. So instead of looking at the distribution of grade point average, I'm looking at the distribution of the average, grade point average. The distribution of grade point averages might go from 0 to 4, but the distribution of the average will be tighter. But this is the cool thing. When it comes to sampling distributions or looking at the distributions of statistics, so we're not looking at the distribution of the individual grade point averages. I can look at the entire population of grade point averages and I'll solve for the standard deviation and it'll be high. But if I solve for the standard error of the population mean or the standard deviation of the sample statistic, the mean, that measure of dispersion will be lower than the measure of dispersion for the individual values, which is interesting. So essentially what I'm saying is, not only can I look at how the individual values of a variable are distributed, but I can look at how the values of a statistic are distributed. I just have to sample over and over and over again. For each sample, solve for the statistic, in this case the mean, and then look at those means, look at how they're distributed. That's called a sampling distribution. And again, an important result is that the mean of a sampling distribution is equal to the population mean. In other words, the mean of the sampling distribution will be equal to the population mean. So you can take some more advanced statistics classes and actually prove that to yourself. You can prove it by hand or prove it through simulations, but it's really neat. It's a neat result. And the sampling distribution of the mean, so if we take sample after sample after sample and solve for those means and we look at the distribution, they will be normally distributed, even if the individual values of the variable are not normally distributed. So even if the population values are not normally distributed, the distribution of the statistic, the mean, will be normally distributed. Very quickly, the population of all possible sample means has, well, to get this 100 minus, to get the 95% confidence interval, we have to review some pretty important results. We already know how to solve for the interval, but just very quickly, if we look at the sampling distribution, the average of the averages, so if I take the average of the sample means, I will get the true population mean. The sampling distribution has a variance equal to sigma squared divided by n. So the variance of the sampling distribution, or the variance of the distribution of sample means, is sigma squared divided by n. So we have a standard deviation of the sample means equal to sigma divided by root n. And again, the population of the sample means, or I'm sorry, the sampling distribution has a normal distribution. So the average of the sample means will equal the true population average. The variance of the sample means equals the true population variance divided by n. So if I take the square root of that, the standard deviation of the population means, this is also called the standard error of the mean, is equal to sigma divided by root n. That's kind of familiar. And the distribution of the means, so the distribution of the y bars, is normal. So you can tackle example 4 when you get a chance, but it states that if the true values of mu, sigma squared, and sigma are 31.5, 0.64, and 0.8. So let's say mu is equal to 31.5. Let's say that sigma squared is equal to 0.64, and let's say sigma is equal to 0.8. The question is, what are the values for the average of the averages, the variance of the averages, the variance of the sample statistic, and then the standard deviation of the sample statistic? So given this information, what are those values? And again, you can solve for them on your own. We know that the average of the average equals the true population average, so that's 31.5. And we know that sigma divided by root n is equal to the standard error of the mean. So 0.8 divided by, we said n equals 5 from before, so 0.8 divided by 5, 0.8 divided by, not 5, the square root of 5, and that gives us 0.358. So that's the answer to that question, and that question is in the notes. So if we assume that the population of all mileages is normally distributed, if this is the case, then the population of all possible sample means is also normally distributed. Even if the population of all mileage is not normally distributed, the population of all possible sample means is likely normally distributed. That's the result, the statistical result that comes out of the central limit theorem. So let's say we want to know what the 95.44% confidence interval is. Well, we know about the standard normal distribution. We know that that mean of means plus or minus 2 standard deviations, those are the standard deviations of the means, or the standard errors, that is going to equal 31.5 plus or minus 2, we've already solved for this, 2 multiplied by, what was it, 0.358, and then this gives us an interval 30.784 to about 32.216. So what does that mean? Well, we know that under a standard normal distribution, we're not working with the t, we're working with the z value now, in between -2 and +2 standard deviations. Remember, we did that already. In between -2 and +2 standard deviations, we get 95.44% under the curve. So 95, the result is this. The area between -2 and +2 is 95.44% under the curve. I could look at a z-table to find this information out. I just used theta. So what's the result? Thus, 95.44% of all possible sample means lie in the interval 30.784 to 32.216. So 95% of all possible sample means lie in that interval. So basically what we're saying is that if the population that is sampled is normally distributed, then the population of all possible values of the sample mean minus the average of the averages of the true sample mean divided by the standard error is equal to y bar minus mu divided by sigma divided by root n. So again, if the population that is sampled is normally distributed, then the population of all possible values of this has a standard normal distribution. Basically what we're saying is that our sample statistic, the sample mean, which is y bar, the sample mean, we can normalize it. We can subtract out the true mean and divide by the standard deviation, and we'll see that it is also distributed normally. Now, if I look at the distribution of the means, it's going to be tighter than the distribution of the individual values. So again, in the context of grade point average, if I look at the distribution of all GPAs of all students, it's going to be a wider distribution than if I look at the distribution of the means. So the means will sort of average out the really high GPAs and the really low GPAs. It'll take this very dispersed measure of individual values and tighten them up a bit. But the point is this sample statistic is centered on the true value, and I can use that result to make probability statements that make it possible to infer information about the population from the sample. So let's say we are not working with the true population standard deviation. Let's say that we have to estimate that with a sample standard deviation. It can be proved that if the population that is sampled is normally distributed, the population of all possible values of y bar minus mu divided by s sub y bar, which is just y bar minus mu divided by s divided by root n, has a t distribution. So when we know the population standard deviation, we've got a normal distribution. When we don't know the population standard deviation, we've got a t distribution. But this statistic, again, this is just like a z value, but it's called a t value. This is a t value. So for each mean, I can map it to a t value, and those t values are, you guessed it, t distributed. They follow a t distribution, which is kind of like a normal distribution. Instead of having tails that nearly touch the mean, the t distribution has tails that are a little bit farther away from the mean. So again, if the population is normally distributed, the population of all possible values of the t value, the standardized or the normalized population means using the sample standard deviation, that's going to be t distributed with n minus 1 degrees of freedom. So this sort of implies that, oh good, I'll be able to fit it here. This implies that the probability, let me write that over, the probability of getting a t value, so y bar minus mu divided by s divided by root n, the probability of getting a t value less than or equal to this critical value associated with a particular alpha level and degrees of freedom, which is greater than or equal to this t value, the negative t value associated with that alpha and degrees of freedom. So basically what I'm saying is that I can find this t value, the negative t value, that puts alpha divided by 2 area in the tail with n minus 1 degrees of freedom, and this positive t value, that's an alpha, well, I'll write it over, alpha divided by 2 with n minus 1 degrees of freedom. So if I put, let's say, 2.5% in each tail, 2.5%, and I find those critical t values, then I've got a 95% interval. So if I find these critical t-values by putting 2.5% in each tail of the t-distribution, I can say that some randomly chosen value of the mean lies within that interval 95% of the time. So again, this is a probability equal to 95%. So the probability that this value is greater than or less than the critical t on the lower end and less than or equal to the critical t on the upper end, this probability is equal to 95%. So what I can do is manipulate this result to derive the confidence interval. So again, these are t-values, and the math, I think, is broken down in the notes in more detail. And of course, we're never going to have to derive these intervals. We're just going to be told how to solve for them. But if we wanted to, we could. So we know that the probability that this value is greater than or equal to the lower t and less than or equal to the upper t is 95%. What we can do, so that is equal to 1 minus the alpha level, and we choose that. If we choose a 5% alpha level, essentially what we're saying is that we're going to be 95% confident. 95% confident. So the probability that a particular t-value is greater than the lower critical value, but less than the upper critical value, is 95%. So I can multiply this inequality by this quantity. So I'm multiplying that by that quantity, and then I'm multiplying that by that quantity. And then what I can do is add or subtract the mean from both sides, and then multiply everything by -1 to obtain the confidence interval. So again, if you multiply both sides by s divided by root n, and then you subtract out the mean from both sides, and then you multiply everything through by -1, and remember when you do that, the inequalities switch, but this is the result that you get, and it's the result that we saw from before. But long story short, the confidence interval is solved for as y bar plus or minus the critical t given a particular level of confidence and degrees of freedom, and we're going to do some examples in just a second, all multiplied by s divided by root n. And that gives us the confidence interval for mu. So I can write this a little bit differently. Let me see if it'll fit. So I can put mu, we can manipulate this equation to show that mu is going to be less than or equal to y bar plus the critical t, which is alpha over 2. The critical t depends on the degrees of freedom and the level of significance, times s divided by root n. So the true value is going to be less than or equal to y bar, the sample value, plus that quantity, the critical t, times the standard error. But it's going to be greater than or equal to y bar minus the critical t, degrees of freedom, multiplied by s divided by root n. So this is equal to 95%. So what we're saying is that the true value, the true mean, lies within this interval, y minus the critical multiplied by the standard error. So y minus the critical multiplied by the standard error to y plus the critical t value multiplied by the standard. The true value lies in this interval 95% of the time. So we can say something about how close our sample statistic is to the true value given some critical t value that depends on the degrees of freedom and the level of alpha. So again, just going through the notes, it says that the proportion of confidence intervals containing the population mean mu in the population of all possible 95% confidence intervals for mu is equal to 1 minus alpha, or 0.95. So basically 95%, the proportion, 95% of all confidence intervals that we estimate will contain the population value mu, which is neat. So once we estimate a confidence interval, we can say that, 95% of the time that interval will contain the true value. That's a little bit different than saying that the proportion of confidence intervals containing the true value in the population of all possible 95% confidence intervals for the true value is equal to 95%. But that's sort of like, those are logic statements. For all practical purposes, when we solve the confidence interval, 95% of the time the true mean is going to be in that confidence interval. So we've got that neat result, y bar plus or minus the critical value multiplied by the standard error. So that means that 95% of the confidence intervals in the population of all possible 95% confidence intervals for the true value mu contain mu. And 95% of the confidence intervals in this population, and 5% of the confidence intervals in this population do not contain mu. But the main thing is 95% of the confidence intervals in the population of all possible 95% confidence intervals for mu contain mu. That's the big result. So let's move on to confidence intervals based on the normal distribution. And I think that in between, from here on, it'll go by pretty fast. So as you know, this example is based on the t distribution, and it assumes that the population sampled is normal. The t distribution, we're working with a small sample, but we can now consider a confidence interval that is valid for any population. The math is pretty much the same with a couple of slight differences. But the central limit theorem, and we've talked about it already, basically says that if the sample size is large, and when we say large, basically what we mean is, larger than 30, then the population of all possible sample means is approximately normal, with the average of the sampled, the average of the averages equal to the true population average. So if I take the sampling distribution of the mean, or if I take the average of all of the sampled means, that's going to equal the true average, and the standard deviation is going to equal sigma divided by root n. So that's the standard deviation of the sampling distribution, or the standard error of the mean. So basically what the central limit theorem is saying is that if n is big, we can use the z's instead of the t's, that the mean follows, that the average of the average is equal to the true mean. It's unbiased, basically, and that the standard deviation is equal to sigma divided by root n. So if n is large, the population of all values of this quantity, y bar minus the true divided by the standard deviation, has a standard normal distribution. So this basically means that y plus or minus the critical z, and again, this all depends on our chosen level of significance, so that's alpha divided by 2, divided by the standard error of the mean. So this implies that these quantities, y bar plus or minus z, alpha divided by 2, and then suppose we're working with the sample standard deviation instead of the population standard deviation, that both of these quantities are 95% confidence intervals for mu. So both are 95% confidence intervals for mu, and this is when we have a sample size greater than 30. Again, we can derive these intervals using a similar process as before, but that's not necessary. You can play around with that if you'd like, but you're going to end up with the same result. So in summary, when we do not know the population standard deviation, we should use this confidence interval. When we do not know the population standard deviation, if, this is the big one, if, I'm going to put two F's, if and only if, n is greater than 30. So if we have a large sample, we can use that formula to solve for the confidence interval. And if the sample is small, we are going to use a different formula. We've already seen it. It's just based on the t. So if we don't have the population standard deviation, we use this if we've got a large sample, or we use the yellow if we've got a small sample. All right, moving on to